Good. Fine. So I just realized that we're going very slowly with this Blackboard, so I have to sort of try and pick up some speed. So we've seen yesterday, finally, the shape of the function, okay, g of the progress variable, g of psi, as a function of the progress variable for one reaction, right? Now, let's try now to come up with an expression that we can use invariably all the time for a given reaction to find the actual composition of equilibrium, okay? So remember that the condition of equilibrium, so we go back to the generic condition of equilibrium at a certain temperature and pressure, okay, which was, if you remember, this expression here. This is I, is equal to 0, okay? So that's our condition, and so for one generic reaction, okay, we're going to have, as you will see, many independent reactions. In fact, if you remember that each reaction, okay, well, by the way, if you want to see my face, I don't know whether that's a plus or not, but here. If you want to know how many reactions there are that are independent, remember that each reaction is a vector, okay, in the composition space, and it's actually a basis of the null space of the matrix A, okay, or the kernel of the matrix A. It turns out that the dimension of the kernel of A is the number of species minus the number of reactions. We'll see that, but in case you're wondering how many different independent reactions there are, well, they're in a number which is equal to the number of species minus the number of reactions. The number of species minus the number of elements, sorry. That's the number of how many different reactions you can have in a system, okay? So this is the number of atoms, and this is the number of molecular species. Anyway, we'll get to that in a second. So for one reaction, okay, generic, which is like written as usual like this, okay, we know that we can write D and I, okay, we wrote it many times, as the difference in stoichiometric coefficients, okay, times the differential of the progress variable, okay? So again, long story short, dg can be written as essentially this expression here, okay? And so the condition here becomes a stationary point or a minimum point of this graph here, which is expressed as this quantity, mu times the difference in stoichiometric coefficients equals to 0, okay? So this is the minimum point of the graph we drew yesterday, okay? Now we can do, we can take a step further, because we know that the chemical potential has an expression, okay? Standard state, okay, for the pure species plus, that would be RT logarithm of xi, okay? Here. And so we can substitute this here, and this will be a condition, okay, of equilibrium. So that would be mu I 0 plus RT logarithm of the mole fraction, okay, times the difference in stoichiometric coefficients. Again, we're considering just one reaction, this one here, okay? That is equal to 0. Bear in mind that this is a condition of equilibrium, okay? Of chemical equilibrium. Therefore, if you look closely, this composition here, okay, xi in terms of mole fraction is really the equilibrium composition, okay? So bear this in mind. What do we do with this expression? Well, let's split this expression so that on the right-hand side, we have essentially everything that is dependent upon essentially temperature, okay? So we're going to have the factor 1 over RT, which multiplies essentially this quantity here. Okay, remember that this is a function of temperature here. This is a function of temperature. And on the left-hand side, we are left with still the difference in stoichiometric coefficients, okay, times the logarithm, the natural logarithm of the mole fractions. Okay? So this essentially is a function of the equilibrium, or essentially represents the equilibrium composition, okay? And this is essentially a function of temperature, okay? Well, first of all, this is a nice achievement because if we can write down an independent reaction, for each of the independent reaction, I can write down something like this. Okay? So at least I have a set of equations that I can use to find my composition of equilibrium. Bear in mind that the unknowns in the composition of equilibrium are x1, x2, x, and s, right? So I have ns unknowns, okay? So I will need potentially ns equations, okay? This is one of them, okay, clearly. Let me just write down explicitly the mole fraction as essentially a ratio of the partial pressure of species I divided by some reference pressure, which could be, for example, 1 atmosphere, okay? And this, let me add this, the subscript equilibrium here to remind me that this is really, again, as I said here, the composition of equilibrium, okay? In fact, being a logarithm here, a natural logarithm, I can have this factor here be brought up as a power, okay? So this would be logarithm of pi as a power of the difference of stoichiometric coefficients for species I, okay? And if you remember that, I'll write it over here, the sums of the logarithms, okay, is equal to the logarithm of the products, okay? We can write this, okay, as the logarithm, the natural logarithm of the product, okay, over I of these quantities here. right? So let me rewrite this. So this is this term here, okay? And well, this is equal to this term here, okay? So let me rewrite this by taking the exponential now, okay? So I get rid of this natural logarithm, and I have that the product, okay, of the ratio pi over some reference pressure, total pressure, at equilibrium, okay, to the power of the difference in stoichiometric coefficients, okay, is equal to, I'm taking now the exponential on both sides, okay, so it's the exponential of minus 1 over RT times this quantity here, which, by the way, we have seen already, and I'll remind you. Okay, let's see what this quantity is, in fact, okay? Especially this quantity here. Well, if you remember that G can be expressed as through Euler's theorem like this, okay? Then essentially, when we write down this quantity, this will be essentially what? The sum of, whoops, sorry. Of ni double prime times mu I0 minus ni prime mu I0. So what this means, okay, just like this, it's essentially the standard state Gibbs energy of, you see here, you have product number of moles here. So you have of the standard state Gibbs energy of the unmixed products, okay? And this is the standard states of the unmixed reactants. Okay, this is only one prime. So again, this will be equal to something that we've already seen yesterday, delta G0. Okay, at some temperature and reference pressure, which we can consider to be just the unit atmosphere. Okay. Now, if you remember, if you go back couple of pages, I'll get back to this. Let me scroll up a second. The delta G0 essentially was, remember this quantity here, okay? So you take the products, you take the reactants, okay? So this is essentially the difference between, as you see, the unmixed reactants. In this case, we only had one unmixed products, we only had one product, and the unmixed reactants, that we had two reactants here. The difference is delta G0, okay? And we saw that it had a very important role in shifting this equilibrium point left and right, because you see, if for delta G, which tends to be negative, we saw that this minimum point tends to favor the products. It shifts to the right, and we'll try and rationalize this, okay, more clearly today. Okay, so the fact that it appears here, it's no surprise, because it will essentially play a very important role in the determination of the equilibrium point. So let's rewrite, okay, the above equation. So we have the product of the partial pressures, okay, to this exponent. This is clearly the composition of equilibrium, okay, is equal to the exponential at this point of a very much simpler expression, because we have 1 over RT times delta G0. Okay, and this quantity here is what we refer to as the equilibrium constant. Now, the constant part is a misnomer. It's not, because it's not constant. I mean, it's a function of temperature. So we can call this Kp of T. Okay, and this is something that is related here to the equilibrium composition, and it's called sometimes found as the reaction quotient. I'll tell you why it's a quotient in a second. So if we have a temperature here, definitely we can compute this number. This is a constant in that sense, okay? It's a number. And for any pressure, we'll see how in a second, okay? We can therefore find the equilibrium composition if we have enough, obviously, enough equations of this kind. Now, as I said, I mean, this is a reference quantity, so we can we may as well put a 1 here to signify that it's 1 atmosphere. So essentially the quotient here becomes this quantity here. So you see that we have essentially products of a numerator and a denominator, essentially, okay? Because you see we have an exponent here which is positive and then an exponent which is negative. So we can rewrite this in the following way. So the partial pressure of species 1 to the power of knee prime, knee double prime, sorry, plus the partial pressure P of species 2 times knee double prime 2, etc. Okay, up to the last species. Okay, divided by, again, all the products of the partial pressures, okay, to the power of the knee primes, okay? So that's the quotient, okay? So the actual definition, okay? So given a chemical system and one reaction, we have identified, okay, the set of partial pressures that is consistent with a condition of equilibrium. So again, if you want to rewrite this, it would be something like this. Okay, I'm just rewriting, etc., etc. Okay, this is the condition of equilibrium. So all of these are partial pressures of equilibrium. Okay, this must be equal to this constant here, Kt. And I'll remind you that Kt is by definition, okay, the exponential of minus delta G0 divided by RT. So I give you the temperature, you calculate this number, you put it on the right-hand side, okay, and you have a relationship between all these partial pressures, okay? obviously a nonlinear relation, okay? Indeed, okay, if we keep the same standard state, you see now essentially the standard state is buried in here, we can really carry out or use this relation here between the partial pressures and the equilibrium constant at any total pressure. Any total pressure P, where essentially we know that Pi is equal to the mole fraction times P, okay? So in fact, we can even write this in terms of the mole fraction, like this. So let me write it in short as the product of the Pi to the power of the difference of stoichiometric coefficients, okay? This can be written as, if Pi is again xi times P, we take the P out. So this is the total pressure, which could be 10 bar, 20 bar, whatever pressure you're using. Because there is a product here, the exponent now of the pressure is the summation, okay, of these differences, okay, on all species, okay, times now the product, and now instead of the partial pressures we have, so this would be the equilibrium, okay, we have the mole fractions, okay, of equilibrium, okay, to the power of n double prime minus n, okay? And this, again, must be equal to the constant, equilibrium constant. I was thinking, I paused because the common mistake or conceptual mistake that one makes is that in writing this, one would say, oh, the equilibrium constant is defined as this guy here. No, the equilibrium constant is this, okay? This is the definition, okay? So I should even go ahead. I mean, I write KT for short, okay? But in fact, it's the exponential of delta G0 RT, okay? This is what KT is, okay? And that is equal to this expression here. Think that in general, the equilibrium composition is a function of pressure as well, because pressure appears here. So this quantity is not a function of P. It's only a function of temperature. Can you hear me?
Yes, Professor.
Okay, great. You can't?
Yes, Professor, we can hear you.
Okay. Obviously, this is a function of pressure. Obviously, this is also a function of pressure. Otherwise, you wouldn't be able to have a function which is only a function of temperature. So this is also a function of temperature, which proves, all right, I said temperature, but I meant pressure. So I'll try to explain this again. The equilibrium constant is only a function of temperature, okay, not a function of pressure. But if you look here, you have what? Pressure appearing here. So the overall expression cannot be a function of pressure. Therefore, this must be a function of pressure as well, which proves that, generally speaking, clearly, the equilibrium composition is clearly a function of both temperature and pressure, okay? There is a particular case, if you look at this expression, what if this number here, the exponent of the pressure, right? What if it's zero? It could be zero. And there is no reason why it shouldn't. If you see this exponent of pressure is actually 0, well, you see that the actual total pressure at which you're carrying out the reaction, okay, disappears from the equation, which means essentially that the equilibrium composition cannot be a function of pressure anymore, okay? And this is an interesting aspect, which I'm going to return to if I have time today. Okay, let me analyze a little bit this function here, which by definition, so the equilibrium constant, okay, which by definition is the exponential of minus delta G0 divided by RT, right? Now, first of all, if you want to graph it, well, the logarithm of Kp is really a line, okay? As a function of delta G0. So one way to look at this, okay, at this expression is on a log scale, like this, as a function of delta G0. Because if I, so this would be logarithm of Kp. And this is essentially, you see a line with a negative slope, like, oops, like this, okay? Now, why is this important? Well, when delta G0 is equal to 0, so we have a 0 here, because there's a logarithm here, we have that Kp is equal to 1, okay? And on the right side of this 0 here, you have the delta G is bigger than 0. So you see essentially that for each, whenever delta G0 is bigger than 0, you have that you're in this Kp less than 1 domain. Okay. On the other hand, if you're on this side here, you're in the negative side of delta G0, you see that Kp tends to be bigger than 1. Okay? Now, remember that the condition of equilibrium is that Kp must be equal to the quotient, right? Which is essentially all of the species essentially elevated to the stoichiometric coefficients of the products. Okay, there's a double on the right side of the equation, so there is a double prime here. So you expect, essentially, you expect the species to appear in the numerator as being products, not reactants, because reactants have a 0 here as a Ni double prime. On the other hand, the reactants will appear in the denominator because they're elevated to the single prime stoichiometric coefficient, okay? So generally speaking, sorry, this is single prime. So generally speaking, what I'm saying is that on this quotient, you have products at the top and reactants at the bottom, okay, in their equilibrium composition, okay? I hope you agree. So now look at this graph that we just wrote. Well, if delta G0 is bigger than 0, then we know that Kp is less than 1, right? But look at this equation here, the equation of equilibrium, the statement of equilibrium, okay? If this is smaller than 1, and this ratio is smaller than 1, that means that at equilibrium, because this ratio is smaller than 1, okay, the reaction will favor what? It will favor reactants. So this is bigger than this, clearly, okay? Okay? On the other hand, if delta G0 is less than 0, okay, Kp is clearly bigger than 1, so at equilibrium, the reaction favors products. Okay? Again, why? Because Kp is essentially, at equilibrium, is the ratio between products and reactants. Okay? So if this is smaller than 1, okay, you have reactants that are essentially in a concentration that is higher than products. Okay, so the denominator is higher than the product, so you have smaller than 1. If it's bigger than 1, it's the opposite. Okay? And this is exactly what we saw at the end of yesterday's lecture, when for a single reaction we had drawn the function g of psi, right? So for that reaction, remember, there was essentially a standard state Gibbs energy of the unmixed reactants, okay? And if your products are over here, so if G0 of the products, of the unmixed products is over here, we saw that the shape of the Gibbs energy function, okay, as a function of psi, was so that the progress variable of equilibrium was more on the left side, okay? And this is exactly what we saw here in this particular case. Clearly, delta G 0 is positive. So it's this case here, okay? If delta G 0 is positive, Kp is negative, and the reaction will tend to favor the reactants. You see it's more shifted towards the left. On the other hand, if your products, say, are over here, then clearly your delta G0 is negative, right? And so this function will have its minimum clearly a little bit, far more shifted here. This is the minimum to the right side. Okay, so you see that by moving this point, for example, up and down, clearly you're not just moving this point, you could be moving this point as well. What's important is the delta G, the jump, okay, in Gibbs energy of the unmixed products and the unmixed reactants. Okay, that's why it plays a crucial role. Okay, because essentially it defines, okay, the equilibrium constant. Okay, and really the equilibrium constant is fully related to delta G0 in this way. Okay. So that's another thing that we understood. Okay. And I hope you're not confused in that we took it really step by step. Okay, so now everything should be quite clear how we got to writing down this function g of psi, and now we also wrote down a condition of equilibrium, and we related the two essentially. I'd like you to understand another final thing, which is the role of this exponent here. So let me go back a little bit. You see that this particular exponent is a pressure exponent. And if it turns out that the sum of the differences for all species, okay, of the stoichiometric coefficient is 0, well, then the equilibrium composition does not depend on pressure. This term here vanishes, okay, becomes 1. But physically, why is that? Well, so let's see what the meaning of it is. So in general, we know that we can express for each species the number of moles as the initial number of moles plus the difference in stoichiometric coefficients. This is clearly for one reaction, okay, times psi. And really the total number of moles, okay, of all the species is just a summation, okay, of Ni, right? So the total number of moles is, using this expression, is the sum of the initial number of moles on all the species, Ni, okay, plus the progress variable times exactly this quantity that we're interested in, okay, the sum of the difference of the stoichiometric coefficients. Okay, we're going to call this, for example, alpha. It's a number, right? So if I give you a reaction, you can calculate this. Okay. Now, if this number alpha is equal to 0, for example, well, then the total number of moles, you see, it's simply equal to the sum of the initial number of moles, okay? And so it's constant. It does not depend on psi. It does not depend on whether the reaction is more shifted to the left or to the right. Bear in mind here, we're not talking about the number of moles of atoms, okay? That is always constant, okay? This is the number of moles of species, okay, which may not be constant, okay? Now, if alpha is 0, this summation of the difference of the stoichiometric coefficients is 0, then clearly the total number of moles remains constant, okay? So that means essentially that the reaction occurs at constant number of moles. Whatever happens, if it shifts more to the right or to the left, the overall number of moles stays constant. And that's physically a rather important thing to say. So let's rewrite this as so total number of moles as the sum of the total number of initial moles, okay, plus psi alpha, right? So alpha, generally speaking, could be, for example, bigger than 0, alpha, okay? It could be equal to 0, or it could be less than 0. It's a number, right? So this means essentially that if alpha is bigger than 0, okay, as the reaction proceeds from left to right, okay, I can represent the direction here as, so as psi increases, then n total increases. Here n total is constant, and here, as again, as you go from left to right and psi increases, the total number of moles decreases. Why is this important? Well, look at the equation of state. You have that pressure is equal to number of moles, okay? In a mixture, this is the total number of moles, clearly, RT over V. So if we write this using this expression, okay, this could be the total initial number of moles, okay? So we have the total initial number of moles plus psi alpha RT over V, okay? So if you keep the temperature and volume constant, for example, okay, and alpha is positive, is bigger than 0, then as the reaction shifts from left to right and psi increases, the pressure increases. Why is that? Well, because you're producing moles. You're increasing the number of moles, okay? The overall number of moles, or if you want, the overall number of molecules in the system, okay? And so there are more molecules in the unit volume at constant temperature, and so the pressure will increase, okay? Now, in the last 3 minutes, so I hope this is clear, okay? We're always conserving atoms. Forget that. That's always guaranteed. What we're not conserving is clearly the total number of moles, okay? You could produce, for example, for one molecule, you could produce 2, okay? In a particular reaction. And clearly this will be related to a change in pressure, okay? Now, this is related to an important concept, which is sometimes called the Le Chatelier principle, which really relates this number alpha to whether a system will respond to, for example, an increase in pressure, okay, by, for example, decreasing psi or shifting from right to left. Now, I will just give you a hint and then we'll prove it later on. But suppose that we have a chemical equilibrium, okay? And suppose that we perturb the system, as we usually do, right? By, in this case, increasing the pressure. We want to increase the pressure. How do we do that? With mobile walls, okay? Now, we have perturbed the system from a condition of equilibrium, which is a minimum of Gibbs energy, right? So once we perturb the system, the Gibbs energy goes up. It will increase, right? Now, suppose that alpha is 0, okay? If we now release the constraint, okay, meaning we let the system evolve naturally, keeping this pressure, this high pressure that we have increased, okay, we have to expect that the system will relax towards a new equilibrium, okay, a new composition. And, well, we just saw that an increase in pressure had increased Gibbs energy, so the system will essentially respond in the opposite direction, okay? It will respond so as to, in a direction that tends to decrease the pressure. Clearly, the pressure stays the same, so what happens is that the system will automatically respond so that if alpha is positive, psi will decrease, because if you remember here, when alpha is positive, an increase in alpha translates into an increase in pressure. So it will be the opposite, okay? Psi will decrease for alpha bigger than 0. So in essence, what we're just saying, quite an obvious thing, is that the system will spontaneously counteract, okay? So that it will tend to go back to a minimum of Gibbs energy, okay? So if we have increased the Gibbs energy by increasing the pressure, the equilibrium will shift to the left. okay? Had it shift to the right, the Gibbs energy would have tended to increase even further, okay? So next time we're going to do a couple of examples just to clarify this, okay? And then after that, I just want to finish with the chemical equilibrium by giving you a full exercise, okay? When we put all the pieces together, and then we'll move, hopefully, to part 2 of the course, okay? Which is chemical kinetics, okay? So it's 2 o'clock, so we can stop it there.